Hello, hi, good morning, afternoon, whatever it might be. My name's Geoff Huston. I work with APNIC, and firstly, I must say I'm sorry I'm not with you in person. It seems to be so close to time to travel, but just not quite yet. So, unfortunately, it's video time. I do it live, but it'll be 2 o'clock in the morning. And there are many things I can do at 2 o'clock in the morning. Actually, no, they're not. I only sleep at that time. So I'll record this instead. And today I want to talk about Ipv6 and fragmentation. So let me share this screen and head on with a presentation pack. I'm sure most of you are aware that what we selected as V6, so many years ago, 94, I think, was actually the proposal that made the minimal amount of change to the existing V4 structure. So there are a small number of fields in the IPv4 header that changed, the identification field, the fragmentation control field, the protocol number. They all got moved out of the header, and in its place was the flow ID. So that was the summary of the changes, which seems relatively minor. To go into a little bit more detail, the original type of service field in V4 that, quite frankly, we never found a use for. Even, inserv and diffserv never quite got there. And ECN is still sort of partially implemented. So we've now changed this to traffic class because that'll be implemented so much better, or not. We added a flow label, and then we never quite figured out why. To be perfectly frank, it's yet to find a useful role, if indeed it ever will. The header checksum was pushed down a layer, and all those other fields were actually replaced by chained extension headers. And so the packet ID and all those fragmentation controls, they became an extension header. And in some ways, that was big. Because if there's one thing that IPv4 had as an asset that no other protocol at the time really managed to do, it was adaptive control of the packet size. Because at the time, and I'm talking in the 1980s and even late 70s, each time we defined a new media layer, we kind of defined a range of packet sizes that were supported. Many of you are familiar with Ethernet, minimum size 64 bytes, maximum size 1500. But when we moved to FDDI, the maximum size was 4000 and so on. So if I'm going to build an inter-network that joins a FDDI network to an Ethernet network, what do I do with all those packets that have size 4000 octets? Well, in V4, it's kind of, well, that's easy. I will take out my handy packet slicer and dicer, and I will chop it up so that it fits into 1500 octet fragments, put the common IP packet header on all of them, set the fragmentation control bits, and send it on. Now, in V6, we changed that. We changed it to where those fragmentation control bits fit. They're in an optional extension header. No fragmentation, no extension header. And we changed who could do it. Routers were no longer allowed to do that adaptive slicing and dicing. When this FDDI packet hit that Ethernet segment and it was too big, the router in the middle said, oh, I've got a problem. And it sends an ICMP, a control message protocol, back towards the source saying, hey, don't send these packets that are that big. I know it's FDDI, but keep your limit to 1500 and I'll just send them through. And so the whole idea in V6 was that fragmentation happened only at the source, and the control header was for fragmentation was in this optional extension header. Now, it had its problems. And when folks sort of seriously started to look at this, and yes, it took us a while, it took us, I hesitate to say it, but 20 years to actually start testing how well does this work in practice. RFC 7872 came out and actually tested V6 packets using some of these extension headers and looking at their success rate. And so they did fragmentation headers. They fragmented the packet down to 512 bytes and found that generally web, mail, DNS name servers, the drop rate was astonishingly high. 1 in 3, 1 in 2 packets got dropped. And, you know, the other options in V6, the so-called destination options and hop by hop options, were kind of a mixed result as well. Somewhere between 10 and 40% for the web servers, even worse for mail and worse for the DNS. So this is bad. Why is that drop rate so high? Well, for fragments, there's actually a double problem, because fragments were always seen as a bit of a conundrum for security, because the firewall likes to look one level deep and look inside the transport header. It looks at that protocol port number going, you seem to be doing electronic mail. You seem to be using port number 25, whatever. My rule says yes, or my rule says no. And so a lot of that sort of security control is based on the transport header. And if the fragment doesn't have a transport header, the trailing fragments, because they don't, you can either let them all through, that's a problem, or you can drop them. From a security view perspective, that's great. From a fragmentation perspective, it's kind of tough. And that's a problem. So fragments are always frowned upon. That whole Ipv6 message back to the source, it's unvalidated, isn't it? Some random bozo off the network sends you a packet going, hey, that packet you sent was too big. Why should you believe it? Where's the credentials of the sender? It's just a random packet. And so for some reason, I think it's a good reason, ICMP is often just dropped as insecure, and I can understand that. And the other problem, of course, is extension header chains are about as bad as variably sized addresses in terms of architectures, because as soon as you're doing a high-speed engine and some fields in the packet aren't at a known offset, you've got to follow a chain, then what I'm really saying is you've got to do multiple memory lookups. Now, memory hasn't really got that much faster. The cycle speed of memory, the clock times, haven't really changed for the last 10, 15 years. And if you're a high capacity switch and you're trying to deal with 100 million packets per second, that only gives you a few nanoseconds per packet. And if you're going to waste that doing 3, 4, 5, 6 memory lookups, you're going to start discarding packets everywhere. And so this idea of putting the transport protocol header at a variable sized offset from the protocol header was actually a tough place to put it, because that's just additional cycles and performance. And for many switches and routers and sort of transport sensitive devices in the middle of the network, the option was, I either want performance or I want to recognize extension headers. Customers buy performance. They don't really understand this extension header stuff. I'll drop them. And, guess what? They get dropped. Now, that measurement in RFC 7872 that detected this 25, 28% drop rate for fragments actually did it the other way. They sent fragmented packets towards servers and they observed whether the server responded or not. In other words, did you get my fragmented packet? But that's not what we do. We tend to send small packets to servers and the server sends a large response back. And it's the large response that's far more prone to fragmentation. So what we really should be doing is doing it the other way, trying to make the servers send back large packets and alter those servers such that they fragment or put in other kinds of extension headers. So let's try and measure that. Now, I can't change all the Alexa top, whatever servers. I can't. What I can do is set up my own server and enlist a whole bunch of clients to send them requests and then change the nature of the answer such that it includes fragments. And again, by observing the TCP flow, I can actually observe whether that packet gets ACKed if it's TCP, or if it's DNS and I'm sending back a large DNS answer, I can actually tell whether the DNS answer was received or not. So that's the basic architecture of this experiment. We enlist a whole bunch of clients, and the way we do that is by using an online advertisement. we tend to send around 17 to 18 million advertisements a day across most of the internet. They ask for a web object or a DNS query. We generate that from a normal looking back end and then rang it through a packet fragmenter and actually dice with that response and then look at the resulting packet capture to see whether the client got it, see whether they act it in either the protocol way in DNS or in TCP if we're using a web-based system. So we did this test in August 2017, and actually, oddly enough, the results were slightly better. We did 1.6 million experiments at the time and found a 21% drop rate compared to 28%, obviously getting better. We came back to this 4 years later when there's a whole lot more V6 because a huge number of deployments had happened between then and now. And we thought, right, let's set this up again, but let's do this all the time. Let's do this same experiment every day. Now, again, set up that dedicated middle box to fragment the outgoing packets and focus in particular, not on the DNS, but focus on TCP and the web and detect the fact that you didn't get my fragmented packet when you fail to send me back a TCP acknowledgement for that segment, when the TCP session just comes to a screaming halt going, can't do it anymore. And just to test this out a little bit, let's not just always fragment at 1500 or 1280 or somewhere in between. Let's randomly pick a value between 1200 and 1416 octets for the size of that initial fragment. So let's fragment variably and see if size of the fragment has some impact on drop rates. I won't go into detail in the packet mangler design, but let me say that it was a bit of a nightmare. We're using libpcap to detect packets coming in, and that's fine, but it has no buffers. And so you've got very limited time when you're doing a large amount of traffic to actually find the packet, process the packet, and send it on. And so we actually ended up using a whole multi-process situation of doing shared ring buffers. We actually built a complete V6 NAT in the middle of all this. And so we set up a NAT state for incoming packets, and for outgoing packets, we push it through a NAT mangler from that shared NAT state, and also a packet fragmenter that does that, pick a random size and fragment it. And here's the answers. Now, at the start of this year, our experiment platform dropped off the twig a bit, and that data that's shaded isn't reliable data. But over a period of a little over 12 months, the world's average fragmentation drop rate actually got worse for a while, and then has slowly and surely over the last part of 2021 up until today has been slowly and surely getting better. Now, underneath this, you've actually got to understand that right now there's an enormous number more V6 users than there were even a year ago. So in other words, the pool of people being tested is actually increasing rather than decreasing. And so right now, the drop rate today is around 7.5%, as you see in that blue line. If we look at it by country, what you actually find is India is good. A lot of V6 and handling it very well. Parts of the Middle East, amazingly good. Some of the earlier deployments, not so good. France, even Germany, Sweden. And Brazil, again, an early V6 adopter, average, nothing brilliant. So there's a lot of variation, but there's one thing that I suppose should be brought out. The more recent the deployment, the better the numbers. So the more recent equipment that we're fielding in the ISP world seems to handle fragments a whole lot better. Now, I said before that we were varying the fragment size. And so let's look at the drop rate by fragment size. And this is the astonishing surprise, because once we get up over 1370 octets, the drop rate goes from around 8%, 7-8%, up to an astonishing 15%. Huh? That wasn't meant to happen. And when I look at it and divide the world into, are you in America, in Europe, in Asia, then oddly enough, the profile is somewhat different. Europe's kind of bad. Asia also is kind of bad. If you look at Asia, like Europe, the larger packets, it goes all the way up to a 30% drop rate, whereas America is more even. It's still quite high, but it's more even across the sizes. Why? Well, I think we're assuming that every ISP is the same, and they're not. If you're a customer of Telus in Canada, you don't get fragments. You just don't. Look at that blue line. It's a 95% drop rate. I think the only folk who are actually able to do some kind of fragmentation are the residual folks still using some kind of legacy V6 tunneling in V4 that supports some kind of fragment facility. Because at native mode, Telus, everything gets dropped. Whereas a massive deployment in India, Bharti Mobile, which has literally hundreds of millions of customers, has an astonishingly low drop rate at around 4%. Yes, it's getting slightly worse over time, but it's still much better than the world average and still astonishingly low. So it varies a lot by provider. But why else are large packets fragmented? Well, local security policies, maybe. There is this whole issue that extension headers might not be processed in the fast path. And when you go to the slow path, the queues are a lot shorter and the possibility of drop gets a whole lot higher. So large packets encounter a higher drop rate because of slow path processing. Possible. There's this whole issue of path MTU woes. Yes, there is. And I'm kind of also thinking about TCP MSS settings. And the folk that actually receive these large fragments are the folk that set optimistic values for their TCP MSS. And if that value is actually too optimistic, yes, I can handle 1500 octet packets, but in actual fact, you can't. It means that when I try to hand you a large fragment, that packet gets dropped because of MTU. So this whole issue of what am I seeing needs a little more investigation, but it's certainly true pragmatically that the probability of loss increases quite dramatically on average once you get over around 13, 20 octets in packet size. Moral of the story, keep your MSSs low and you'll avoid the problem. Now, I'm kind of wondering, and I think you should be too, is this fragmentation or is this new model of extension header handling in V6? So is it the fact that we've pushed the transport layer down by a certain amount inside this packet and shoved a fragmentation shim in the middle? Or is it just fragmentation? So we then use the technique of what we call an atomic fragment. So we still use that shim, but it says the actual complete packet is just below. So the fragment offset is 0 and the more bits 0. So what it says is, here is a packet and the fragmentation shim header is just filler. It means nothing. And we want to see the drop rate. Now, I'll go back to that original plot that I showed you of day by day, but now let's have a look at that red line, because the red line is the drop rate for atomic fragments. And what we're actually finding is atomic fragments tend to have a drop rate these days of around 6%. And so increasingly it seems maybe the problem is in the extension header, not in fragments per se. Either that or the firewall rules that say, I hate fragments, is so undiscerning and primitive, it simply goes, if there's a fragmentation extension header, just drop this stuff. I don't care if it's an atomic fragment or not, I don't believe it. Which seems a bit crude, but there's a lot of banging the rocks together in networking, so crudity does prevail in a lot of equipment and configs. When we look around the world, again, we see very, very big differences. In Germany, average for all of Germany, the V6 folk there, the atomic fragment drop rate's about the same as the conventional fragmentation drop rate. In Italy, the atomic fragment drop rate is tinsy tiny compared to everything else in normal fragments. And in Australia, the atomic fragment drop rate is higher. Huh? I'm like, I'm getting confused at this point. I mean, it's not as if there are so many different providers of V6 equipment out there. The set of equipment vendors that sell you equipment is actually quite small, and they might do variations in behavior, but these variations are quite dramatic country by country, and probably network by network. And so there's not a consistent story out there about drop rates. You know, sometimes it seems to be the network infrastructure just objecting to extension headers. Sometimes it may well be at the edge objecting to the fact there are fragments. Hard to tell. But this atomic frag data didn't really tell us what we wanted to know. Is it fragments or is it extension headers? So the next thing we looked at is to see what other extension headers are out there. And there are two more that look pretty interesting. We want an extension header that doesn't actually require a behavior, an extension header that just is. And one of them is the destination option padding. Now, in theory, you're meant to have some kind of destination option, a signal to the other end going, I want this packet treated a certain way, here's some additional information, whatever. And you'd like to pad that up to basically a multiple of eight octets to make the offsets all work. And so there's a certain filler that simply goes, I'm just padding, ignore me. So what if we send the destination option that's just, I'm just padding, ignore me. Now, at this point, it looks good because the pad end doesn't do anything. It doesn't rely on any functionality in the host. The network shouldn't actually look at it because it's meant for the end host. So, you know, move along, nothing to see. And so this signaling should just work. And when it gets to the other end host, here's the destination option, but it doesn't say anything. The answer should be fine. Just ignore it and process the packet as normal. Good in theory. What about in practice? Whoa! 94.5% drop rate. I mean, that's bad. And when you get a drop rate like that, and don't forget, way, way back in 2014, what they measured for destination options was somewhere between 10 and 20% drop rate. They did not measure 94.5% drop rate. Something's going on. Now, most hosts don't like extension headers by the look of it, or most networks don't like delivering them, or both. So in some ways, this is a very recent finding, January. We haven't done too much work in trying to look under the hood to find out what's going on, because that's a bad number, but exactly what's going on is still speculation at this point. So let's try again. What if this is all about hosts dropping destination options? Is there another option? Well, yes, there is. It's the same padding option, but this time it's on the hop by hop. Hey, router, if you understand extension headers, look at me. I want you to do nothing because the padding option. And so I'm not asking for any special hop by hop treatment. I'm simply saying, this has got an extension header. Do you like this? And so again, no special processing is being asked for. Should work, right? Right? It's worse. 99.5, you kind of go, if I'd have written a packet dropper, you know, wouldn't be so much different. Everyone doesn't like this option. Most hosts, most routers, somewhere along the line, this is being dropped. So awesomely better. Now, what do we learn from all this? Because this is kind of interesting. The first thing is, slowly and very slowly, we are getting better slightly at handling fragmented V6 packets. It's gone from unusably bad to, you know, tolerably poor. Still not very good. And, you know, the most pragmatic advice to anyone is don't fragment. But more recent deployments are a little bit more robust in handling fragments than older deployments. And destination extension headers and hop by hop extension headers, well, you're dreaming. You're just dreaming. If you're talking about the public internet, these are alien concepts. Public internet, extension headers. don't play. Do not play together. What have we learned about fragmentation? In V6, the answer is you can't, you shouldn't, don't do it. Don't rely on path MTU discovery. Don't rely on extension headers. Don't rely on Ipv6. Just don't. And so if you're setting up a V6 service, pick your MSS in TCP and your MTU size carefully. If you want to go conservative and make sure everything squeezes through, pick 1280. Yes, I know it's a rubbish number and it really doesn't mean anything. But if you want to steer clear of icebergs that destroy your packets, 1280 is a pretty robust choice. If you're worried about that ratio of payload size to header size and you want something a little bit more efficient, you could probably push it as high as 1350 and it would still be survivable. The Goldilocks choice, if it's not too small, but certainly not big enough to encounter problems. Don't go above that, because even as once you get to 1400, the drop rates start increasing as a likelihood of failure. And oddly enough, 1500 is a poor choice, because there's a whole bunch of other middleware equipment that sort of goes, don't like this. Even though 1280 didn't mean anything and 1350 doesn't mean anything, for some reason we've installed a whole bunch of other stuff in the network that actually does do dropping around 1360, 1380 and higher that it shouldn't be doing, but nevertheless it is. You can either pick a fight with them, try and identify each one and clean up this problem. More power to you, but you're going to fail. Or you can set up your own server stacks and client stacks to go, look, if I use 1350, I don't have to fight this fight. It'll just work a whole lot better. And my advice is 1350 is a good answer for quick, for TCP, for anything else. Keep it low, it will probably work. And the lessons learned about hop-by-hop extension headers and destination extension headers, that's easy. Don't use them. They just don't work. As I said at the outset, when we set this thing up a year ago, instead of just running it for a week or so and collecting some data and reporting back, we thought, it might be useful to actually chart progress. And so I do every day. And this URL actually gives you a picture. And the picture is every country, every day. Let me then look at a live view. So we'll stop that sharing and move somewhere else and actually look at what the situation looks like today. Let me now share this screen. And here's what we see as the map of the world today. But we can actually look down further and actually look at, well, how about Oceania? Okay, here's some graphs for how we're doing in my part of the world. How about Australia? There's that atomic fragment. The drop rate's quite high. Real fragments, the drop rate's far lower. Who's doing this? Well, if I actually look at which providers have a large market share in V6, the dominant one, and yesterday, 158 sample points, is AS1221, Telstra. I used to work for them. Let's have a look at Telstra as an individual provider. Overall, their fragmentation drop rate for Telstra customers has been consistent between around 5 to 10% drop rate for the last 12 months. The variations are relatively minor. They might have done something recently in the last few weeks. Hard to tell, it's recent data. The atomic fragment drop rate, they did something in October. They did a software change somewhere in their infrastructure. Atomic frags are bad, let's drop the lot. And so their drop rate for atomic frags is well up around 22.5. Look for your own provider, look for wherever you might be. That web page actually wanders down through every country and every major autonomous system and actually gives you current up-to-date stats on this area of performance of fragmentation and survivability. So that's all I have for this presentation. I will get up at impossibly silly hour of the morning. And if you have any questions, who knows, I might even be awake to answer them. Thank you very much.